Hello everyone, welcome to my shop. I'm Robin. Today we are going to take a 8-inch or 200 millimeter standard 3-jaw non-adjustable chuck and a standard D14 blank mounting plate for mounting the chuck, and we are going to make it adjustable like a buck chuck or a set true chuck, but we're going to address the shortcomings of the standard design of those chucks as far as adjustability, and I'm trying something a little different here, and we'll show the reasons why and all the design choices that went along with it. So let's get to it.
Keep your interest. I'm going to show you this chuck completed and operational. You'll notice the marker is for which adjuster we're working with. 1, 2, 3, 4, and you'll notice they're all sitting on 0, which is with the chuck running true. So this TIR here is, within a half thousand. So now I'm going to move over to this turned diameter here where it is running out. This is my TIR at my number 2 and number 4 locations, which are 180 degrees apart. That's a full 6 thousandths TIR, which means we need to move the chuck 3 thousandths of an inch. So I go to my low side and I back off 3 thousandths. I come to my high side, number 4, and I tighten it to 3 thousandths. Now I come over to the indicator and do my 2 and 4 locations. 2 and 4, you'll notice they're darn close to 0. Now we're going to look at the opposite direction, which is, looks like 1.5 there, roughly 1.5 there, 1.25 maybe. Adjust this so that we're balanced out. Okay, and now we'll go over and we'll make that adjustment, which will be 1.25. I go to my low side, which is 1, back up 1.25, come to 3, tighten it 1.25, and I come over and check the TIR. Pretty darn good. Obviously you can tweak from there. Whole purpose here being that we keep a uniform amount of compression of the chuck body from the adjusters by exactly moving these opposite directions. So why would you want an 8-inch chuck on a Tormach 15-inch Slant Pro? It's because this stock is only 2.5 inches in diameter. With my low speed attachment, this thing can really remove material at that size, not a problem. But this piece is this long, and without being able to swallow that back into the chuck body as the equivalent of having a large through bore chuck, you can't do anything with this. There's no tailstock, so now this is a reasonable length of extension out of the chuck. Chuck's able to grab this with much longer jaw engagement, so now this is very feasible. I'm not really using it for anything horsepower wise, or nothing's changed except this large chuck allows me to hold this piece of stock and machine it effectively.
We're going to start with just general pimping of a chuck that you get. This is a about a $200 or $390 chuck from Char's Tool. One of the important things is it is a ductile iron body. It's semi-steel, ductile iron, whatever you want to call it. It's not a forged steel chuck, but ductile iron is a much better chuck than a cast iron chuck. So this will have a higher RPM rating, max RPM rating, and lots of things like that. And the quality of this chuck, as I'll show, is very good, but still needs deburred and some things tweaked. For the price of these chucks, you can't really expect them to be deburred well. It takes a lot of time and effort to deburr these properly, and all these internal surfaces, every edge, every area, all the outside surfaces, these should be done that you can rub your hand on them forcibly. You have to think about this thing spinning and you happen to bump it with your hands, or you slow the chuck down with your hands. With bad practice, but lots of people do it. You want this so that you can rub this hard and not have anything bite you. So that takes some time to roll the edges, chamfer all these inside edges, all these places everywhere around here which are razor sharp when you get it. These Char's chuck, I have no affiliation with Char's. But I found these to be a pretty high quality chuck, and I'll show you some other details of why I consider that. The scrolls plate is forged and heat treated and ground, so this is not just turned, this is actually ground. And the matching jaw serrations, the teeth of the jaws, are also ground inside and outside. So in general, the actual machine work on these is pretty darn nice for the price. I mean, ridiculously good. But like I said, it still needs an immense amount of deburring. So all these edges here are razor sharp. These are all air tool, you know, all over all these. Rounding these nice. So you need to be able to take this thing and, you know, do this, press it as hard as you can with your hands and not get cut. Because you got to remember, this thing's winging around here, and you might have it where the chuck is, these jaws are poking out of the chuck a little bit, and even if you don't typically touch the chuck when it's spinning, it's still a chance of slipping and bumping into this, and having this deburred that smooth can save you a hospital trip. So just a word to the wise. Another thing is, after you've done your deburring, I use a carbide burr, 70,000 RPM air tool, carbide burr, like a flame point, 1/8 inch diameter, and roll over all these edges. That does a real nice job, and not using abrasives is good because you're not throwing grit all into this thing, and I'm not intentionally not disassembling these jaws. I'm leaving them as factory ground because these are actually ground in place for better TIR than typical. Then a abrasive bristle brush. I have a 6 inch by 1 inch wide one, like maybe 320 grit, and hitting all these edges with that just gives, you know, rolls those edges over even a little bit more after you've done it well with the air tool, and gives you that ability to just, you know, do this. If I did that the way this was when I got it, literally my hand would be in shreds. So this chuck, I will say that a lot of, you know, cheaper Chinese stuff, it looks like they used grease that they scraped off the floor. Grease is clean in this. My only comment is there were places where there was still some ductile iron dust that mixed in with the grease, so it wasn't abrasive and really wouldn't cause any issue. But other than that, this was, you know, quality work on these. And like I said, no connection, just sharing that I've bought several of these. The reason I'm coming back to Shars for this one is because I like the quality of the chucks for the price. Even if you don't do all the deburring I showed, one section that you should pay attention to on jaws is this edge right here. These are hardened, and these were dead sharp before I rounded them on all these edges. And the reason that's important, top, bottom, both ends, is when this jaw is unloaded, it cocks in the slots, as I've shown in my previous video, and those edges can actually chew the iron. It has to be pretty extreme, but it can chew. So you don't want an edge that is capable of chewing the iron, especially when as hard as these jaws are. So make sure, at least if you're deburring, that you at least get those edges broken so they don't chew into your jaw rails. Another place to focus on is the scroll. Getting rid of any razor edges that are on the edge of the scroll, where it's going to start into jaws or might be halfway in a jaw, depending on where it is. So it would be good to make sure that these edges are chamfered and don't have a razor edge, which they had beforehand. So this one's getting hard to get showing. There's the chamfer on that one. And then I deburred all these other outer edges everywhere, especially in here where this is the bearing area of the scroll plate on the chuck body, and this clearance in this area, or lack of clearance there, is what controls how repeatable your chuck is. How much the scroll plate can flop around on that pilot in the chuck body is going to determine how repeatable it moves. And it's also why you always want to use a single pinion location if your chuck has more than one pinion, because the force vector is of that pinion forces the clearance out of the scroll plate in a particular direction. And as long as you tighten it in the exact same pinion each time, it's going to deflect and seat in that same orientation. That makes sure that you're going to get the best repeatability possible. Some people say, oh no, I always was taught that, you know, use all three pinion locations. Well, all three pinion locations, like on a drill chuck, will definitely get your chuck tighter, but it's going to give you inconsistencies in where this thing ends up on that thing, depending on which pinion you ended up on. So if you're out for precision, Don't worry about using all three. Pick one. I mark them on my chucks which one is the pinion to use for tightening. You can loosen it with any of them, but tighten it with the one that's marked. That forces this in a particular vector. Do all your jaw truing, boring of soft jaws, everything you're doing, always do it with that, and preferably torque to some value that you found to be ideal for the chuck, and you're going to get better results. Another topic for chuck pimping is this oiler fitting here. Basically totally worthless. I have no idea why they put it in there. It comes through here to where the chuck scroll face hits, and is basically just going to fill up the scroll plate with grease, which ends up flinging out and flying all over you. So it's really, you don't want heavy grease on the scroll because it's going to collect chips. The place that needs to be lubricated is the actual bearing area here on the chuck where the scroll plate rides, down here. I'm getting a hard time getting that in, good lighting on that, but right down here. So I'm going to plug that, and I'm going to show you, as far as just pimping the chuck, one of the changes we're going to make is we're going to put a grease fitting in here and a grease groove that takes grease out to this bearing area where the scroll plate rides the chuck body, which is the really important place to be lubricated. So we can see from the design of this chuck that this plate, which goes in here, its only purpose is to hold the scroll down. It, in theory, is close to bearing on this flat zone right here, and keeps this scroll plate from, lifting up too high and not engaging with the teeth of the jaws. So, and this is pretty typical. Now, that's the only function this has. It has no structural function to improving the stiffness of this chuck. It's not a press fit out here. It's not doing anything as far as helping the stiffness of the center of the chuck. So I mentioned in the beginning, the whole purpose of this video is to make this into an adjustable chuck. And you could say, well, why don't you just turn, this is about a 14 millimeter step from here to here, and we just saw that plate that on the back is just a protector plate and keeps the scroll plate from being able to flop out of engagement with the jaws. Why don't I just turn a 14 millimeter long shoulder on this, where this diameter here has enough clearance to give some room for the chuck to be able to move on this, and do the normal set screw through the wall, 4 equally spaced opposed set screws that push on the boss on this body, and be done with it. I mean, that looks easy. And then we could have bearing here and bearing here simultaneously. It wouldn't be connected, but it would at least be touching, and it would be quick and dirty. The issue is you have 4 set screws. Each pair is opposing each other and working against each other against the inner hub of the mounting plate, pushing, which basically forces these walls are being forced to expand out this direction. You have the thread screw force this way, the reaction force is out this direction, so this is being pulled, stretched this direction. And this only has limited strength. The fact that it's connected to a roughly circular face plate there, homogeneous material, makes it a little bit better, but I'm going to show you on this next chuck, the amount of deformation that occurs, and this chuck is larger in diameter and thinner wall, so it would be even worse than what I'm going to show you. So here I have the chuck. Here are the the TIR adjusting screws in the chuck are here and here, and I have these just loose. They're just touching, so they're not tight. The back one is touching. I'm sitting on the back of the chuck and the backing plate, and I'm going to come down here with the indicator and show you what happens with the actual reading as I tighten the screw here. So I'm going to tighten this, and you see that's 0.02 of an inch of deformation. I'm actually stretching that ring out of round that far with that force. Now, technically you're not supposed to use that much force on there, but you do have to use reasonably high forces to overcome the friction between the mounting face and the mounting plate and the chuck, because it has to skid. So that's the weakness there. And I'm going to go over to the side, the 90-degree point, and I'm going to actually show you where these sides are actually caving in. I have this one loose, so it can actually, the set screw is not supporting it, and it's actually caving in. And that reaction of pressing on the hoop in one spot and it contracting in the other is sometimes when you tighten two screws, opposing screws, and then you come to the other and you check the other ones, they're tighter than they were. Well, they're tighter than they were because the hoop has been pulled by the other screws, and it has shrunk this up further than it was when you first adjusted it. So it's one of those things where, yeah, there's a reason why it seemed like I didn't think I tightened it that tight. You didn't. The hoop actually deformed in its shape because you tightened the opposite direction screws a little bit tighter, putting more stress in the hoop, pressing tighter on the other set screws. So here I'm set up. This is the same screw I was using. This is a screw that's loose. It's not supporting the wall of the chuck. It's got, the chuck wall has room to move in without bumping into the set screw. I'm going to come up here with the indicator, and I'm going to tighten on the, so I can see me wrenching over here, and I'm going to tighten. You see that sucking in? That's the actual hoop deforming. The pull on this side is stretching that hoop and making it suck in on the sides. So that's the deformations that occur in that. So that's why I'm trying a different arrangement. So my thoughts are, what can I do to stiffen this? Well, I can't do anything to stiffen it in tension. If I put the set screws in the wall still, there's nothing I can do to make this stiffer because the pressures here are going to pull away from whatever I have, unless you put a big external ring on here, which would be impractical. So I'm going to change the direction of forces. I'm not going to put the screws in the chuck. I'm going to put the screws in the edge of the mounting plate. And I'm going to use a relatively large screw at 40 threads per inch so that I have a finer adjustability. I'll show a SolidWorks cross section of this so that it makes more sense. Here's a cross section through the adjuster screw. The adjuster screw has 7/16 40 threads, which is 25 thousandths of an inch lead per turn. We have a 6mm hex, O-ring groove to seal it. The gap here is 4 millimeters, which is the assembled length of the needle thrust assembly to 2 washers and the needle cage. And this side has enough room to clear so that it can move off center. And that's pretty much how it works. As this turns down in, the threads in the chuck body or chuck backing plate allow this to pull down and press on the chuck body, and on the other side you release the adjuster screw the same amount, and you can move off center a relatively accurate prescribed amount. Here's a section through the mounting bolt holes that hold the chuck to the backing plate. Originally this chuck was tapped from the back only, and that was the only mounting that it had, was 6 holes on the outside back of it where the bolts came in from the back through the backing plate into the chuck. I needed to change that orientation so that we had this long neck length of screw where the lateral motions, the column of that screw can just move side to side and not resist the motion of the chuck sliding on the backing plate. So I just drilled through the chuck from the back, counterbored from this side, and then added the 6-hole bolt circle of M6 screws on this side that go through the stiffener plate that we made and into the chuck backing plate. So this is held on at the ID of the chuck and at the OD of the chuck, and both all these screws get relieved so that there's plenty of clearance for this to be able to move sideways. One technique I use for home tooling is to turn the heads of the socket head screws concentric to the shank and the smaller diameter. In this case I use a 1/2 inch diameter for the M8 screws and 3/8 diameter for the M6 screws, and then cut the same diameter with the counterbores. There's only a few thousandths clearance. It makes it very nice for things where coolant gets on them or chips. There's no room for any chips to get in around the outside of the head of the screw. They can only get in the socket, and that's it. So it makes it easier to clean. Just looks more professional. Bottom line is, I'm going to take this piece of steel here, face it off to 5/16 thick, 8 millimeters, and I'm going to make it a light press fit in this diameter here. And it's going to sit down on here. I will put the pieces that are required to have the scroll held in place attach them to the bottom of this so that that all fits, and it'll get the bore to match this bore. But now this cross section, this thick ring, is now forcibly holding this tight, so that the external forces from the adjusters now are being supported by this larger, much larger plate, and this now, the cross section of this in itself is much thicker. Also going to add a 6-hole bolt pattern in here, but not just to hold this plate on. It's going to go clean through the plate and into the mounting plate. And what that will do is keep the face of the chuck from dishing like you saw in my previous video. This will stiffen the face of the chuck immensely. Here I have the chuck body in a vise gently held, and I have my indicator wrapped around the back here, sitting on the front face, reaching through to have a good seat on the face of the chuck. And basically what we're doing here is measuring the amount of how easy it is to compress this. So you see I've got the C-clamp on there. It actually is zeroed released. I have the C-clamp snugged just enough to hold it on there, which is deflecting at 5/10 already. And now I'm going to just give it a good crank here. And that is just moderately tight. So you can see there I've almost deflected this 3.5. I could easily take this to 4 thousandths without any problem. So keep that in mind, because I'm going to show you what that deflection is after we get done putting our pressed in plate. This chuck was designed to have the bolts come in from the back, but that's no good for a set true or buck chuck adjustment, because this surface needs to skid, and obviously if we put this screw in and have this surface bare on the back, there not much skidding is going to go on. It doesn't have any room to move, and this fastener face here would have to skid on the back surface. So as per most chucks that are designed that way, you use a long bolt that has plenty of room to just flex laterally for the few thousandths of an inch of adjustment that you're adjusting, and this bolt can go in the tapped hole and then just flex at the head. This stays stationary, and they're just flexing this long section of bolts. Now, since I'm bolting the inner section of this also to the chuck mounting plate, I have the same situation. I'm going to use a long M6 screw in the on this bolt pattern in here, so that it also can flex. Just a chance to show the collet held stop from my chuck stop video. This is super handy. This lets me go in and just set that quick to be grabbing by just the one lip of the jaw. Another beauty of this is a one-time piece, so I'm not actually putting the stop in there for a repeat position. I'm putting it in there simply to square the part. So, but I need to drill and bore a hole in this, so this is in the way. But I can just pop the collet loose and shift this back out of the way, lock it up again, and I'm ready to go. Here I have the first side on the stop, so I can finish off the other side parallel. Gotta love that CBN tool. Turn the diameter to be a 1/1000th press fit to the inside of the chuck body, and then I did a 1/1000th relief smaller than that, so that could get started square. I have my little 6" by 6" mini pallet in the vise, so that I can hold this chuck face down, and I have it trammed in by bridging across the 2 socket head screws on the threaded section, and just manually manipulating that until it lines up, and then snugging the bolts down. And then I have other strap clamps which are the same size and parallel as spacers, so that when I drill through, I'm not drilling into my pallet. Just a little side note here: when you're drilling a long hole and you want it to stay as straight as possible, ideally you should use like a screw machine drill, something very stiff and short, to drill the initial hole, and then switch to a longer drill. These longer drills, the slenderness ratio, the diameter to length extended, is in the realm where Euler buckling can occur. What that is under high compressive loads, the lateral stability of the column, if you want to call it, gets very rubbery, and buildings have collapsed way back before they were aware of this. So be very gentle. If you're going to use a long drill, be gentle on your feed rate. Don't horse the drill until you get some engagement where that first section of drill, first section of hole is established nice and straight. Then after that, because the hole is now guiding and stabilizing the drill down in the hole, then you can feed a little bit heavier. But just a note that if you wonder why holes wander, it could be because you're horsing on the drill, and what happens is that Euler buckling, when it occurs in the beginning, actually bends and the drill starts to go off in a direction. Once that starts, then it follows in that direction and can get carried away. I've drilled through this bolt circle, the original bolt circle that was used for mounting the chuck, drilled through with a drill larger than 8 millimeters to give this room for the chuck body to move when it's adjusted. But down here at the very end, it's close to on size with the head of the screw. So this has been relieved, this whole section here, so there's plenty of room for this to move uninfluenced. This bolt circle I've added, which is going to have these 6 millimeters coming through from the opposite side, same way as the 8 millimeters. But this is going to screw through my stiffening plate and into the backing plate. So this I believe is going to make this chuck immensely stiffer and for it to dish less under full load than it would without it. So we'll find out. Where the adjusters are going to work and press on this chuck body are in 4 locations, but the axis of them is in this direction. And I was thinking I was just going to grab this in a 3-jaw or a 6-jaw chuck on my indexer and index it, but it's hanging out a lot and not all that rigid, and I thought, wait a minute, if I put a strategic bolt pattern here of 4 dowels that are narrower than my 6-inch chuck jaw width, I can sit on those dowels, put a stop here, get on center one time, and I can literally just index this thing in the chuck and have the ultra rigid setup super fast. That's exactly what I did. These are reamed 8-inch diameter, about 5/16 deep. Here's the modifications to grease the actual bearing surface of the scroll on the chuck. This is the chuck bearing surface here. I drilled a hole through on an angle. This is tapped M3, and then a full diameter that's bigger than M3 a little bit, so it doesn't have any interruptions in the surface, and a chamfer. And that is what mates up with this style of grease gun, plunger style of grease gun. So this goes in, you'll just back the jaws out and press this in, and the action of pressing it in actually seals it. It'll push grease out through this, and then you'll rotate the scroll plate with the chuck key without the jaws in and just spin that around to actually clean that whole area out and grease it well. Here's the plate that is going to stiffen the back of the chuck body, and I'm putting a bolt pattern in now for the holes here are for 3 screws that hold this to the chuck. These 6 holes, this 6-hole pattern is through holes for the 6 M6 screws that are going to hold the center of the chuck back tight to the mounting plate. These holes are for holding the scroll retaining ring in place. This is going to get machined out here. This is going to be just a thin shell of what it was, and this will be held in with 3 M3 screws that go in these holes here.
It's a shame the chuck manufacturer didn't take the opportunity to do what I'm doing with this, which is make the OD of this the press fit inside the chuck body, supporting the outer chuck ring, and just made this a little thicker. So I'm just using this to get this piece out of here so I don't have to make something custom. Bored this to fit the pilot of the chuck body. I'm going to remove this flange because once this is faced down to the correct thickness to attach to my steel plate, none of this flange is going to be left anyhow. Holding this internally to part it off to the correct length. This ring, under any circumstances, is relatively frail because this is all that's going to be left holding a ring. That's why I'm holding it on this side, even though that's where I'm parting. If I held it over here, the chuck pressure would just take this and basically want to snap this off right here. Where here I have a continuous loop, ignoring the flange out here, it's really doing not much other than keeping this section from wanting to bend. It's just a stronger way to grip it, and your forces are right over the jaws, so I just have to be careful to go in and part just till I'm close, and then I'll snap off the rest. You can see here where I just stopped, where it just at the jaws it was able to cut through, and it puffed the inside here, so this should just pop here. Yeah, this is more, I think this is just plain cast iron. The way that cracked right there is a cast, the way cast behaves, not the way that ductile behaves. Here we're using the pallet to drill the 3 tapped holes in the scroll plate capture ring that match up with the back plate. Here I was able to use the dowels in my plate and a parallel to get this thing rotationally oriented before I indicated it in, so handy. Still using the pallet, I have the D14 backing plate on here to do the bolt circles for the screws that hold the chuck to the backing plate, and I'm using a bar, 2 dowel pins to get my alignment to the existing bolt holes. You'll see here that there were some standard holes in the backing plate, and there's one at 180 from that over on the back side that I had to fill up because one of my screws runs into this. So whenever you're doing something like this, you really got to be careful and pay attention to what runs into what, especially when you're adding new features. It pays to have a 3D model, because you can really get bit in the butt where everything looks good and all of a sudden you go to put some feature in, it's like, ah, there's another hole there. And so yeah, foresight beats hindsight by a damn sight. So yeah, think ahead. Now we have our bolt circle out here for the outer bolt circle of the chuck, the inner bolt circle that we've added to the chuck, and we have our all-important 4 equal spaced dowel pin holes that are going to allow us to stage this part in the vise for the angular pockets. This bearing is what presses on the chuck to skid it sideways to make it adjust laterally, but in the process of that, the ones that are at 90 degrees to it see skidding forces this way, and I don't want this race to have a lot of room to flop around sideways because of those forces. So I'm using a functional gauge pin to get the size that will actually work on this. Always a good idea to actually see the number on the pin, not just trust the slot it came out of. And in this case, the actual bearing has a little bit smaller diameter than the race, but that's okay. I just want to make sure that these will fit and as close as possible. Not a good idea for production situations, because there's probably a wide range that these can vary in, but for a one-of in your own shop and you're out for a particular function, nothing wrong with doing that. Here's our adjuster screw, and I'd really like to have a piece of material that was actually forged so that you had grain flow around the corners like this, and it was heat treated to maybe 170,000 tensile strength and properly tempered, and yeah, that would be really nice. And I only want to spend about $3.72 for each piece. That's how you do that. That's exactly what I just described. Forged, professionally heat treated and tempered, 170,000 tensile strength, and this is big enough to get the piece that I need out of there without a bunch of excess material removal. Just a tip for when you need a high strength material and you want it inexpensively. We're using a 7/16 40 tap, and I made a 7/16 40 gauge using this tap, but I made it out of ductile iron similar to what the chuck backing plate is. That's where the threads are going to be. So this I can now use to size my threads on the adjuster screws. Important to have a plan of attack when you use something like this. In this case, I've got 7/16 40 threads down here, which are very, very delicate and fine. So I don't want to clamp on that. I have a 12mm section here, which I can, but I look at this and say, okay, I'm going to grab it on the 3/4 diameter here first. Finish turn this 1/16 diameter here. Use that as my basis for holding this for all these other operations. put the part in and out with a stop so I can drop each one in for each operation. Then once I'm all done that, I can grab on the 12 millimeter in the collet, whack off the excess of this, put in the O-ring groove, and do the hex drill and tap for the hex.
Threading here on the Harding using a full profile insert which tops the thread, which is very handy.
Here's the fit on that. You can see the indicator is definitely touching, and now I'm twisting this back and forth this way, but this still moves free. I'm going in and doing the O-ring groove. I'll pop each piece in, do the groove, and I'll come back and set up chamfer. But all these operations have been done by doing a single operation, put the part in and out of the collet. Groove is chamfered. Now I'm going to part them off about 10 thousandths long. Here's where I ran into the hex, and that's why it popped off. Facing off. Center drill, all 4 pieces, in and out of the collet. Drilling a hole slightly larger than 6 millimeters, so that there's room for the coolant to get out past the broach, so it's not hydraulically locked. This socket head cap screw machines pretty nicely. 6 millimeter rotary broach. Takes some serious pressure. You can see the compacted chips down at the bottom of the hole, and that's why we're going back in with the drill again to get rid of them. There, the chips are removed from the bottom. We need to cut a relief for where the pinion intersects with this plate, interferes, and we're using the bolt holes that are in this already, actually the clearance holes for the screws. We're using those as fixturing, and then I have a stop glued on in the back here that is my locator for lateral. That way I can get on here sideways, get my location here, which is just going to be a visual touch here, and cut an 1/8 inch deep. And then I can just move one of these dowels over to the next hole, get my next index, and carry around to the do all 3 sides. Taking up center, it's not critical in this case because we've got tons of clearance. This is just about eyeball alignment here. I want as large a radius as possible to match the pinion diameter. I just happen to have a tapered end mill that's actually a little bit bigger than the pinion, and but I want the maximum radius size here. So I'm setting my Z here where I still am on a cutting flute. Then I touched the edge and moving in my 1/8 inch from there. So I will be feeding down in Z to cut. I always mark my backing plates for the chucks with a V that matches with the V I've stamped on the spindle nose, so that these are always oriented in the same location. Here we're on the lathe, mounted up and turning the diameters that were required for the chuck system. We've faced this to be true, running true to the spindle. This is relieved to clear the backing plate that we made. This is the correct step height from here to here. In the ballpark, we'll grind the chuck on the other side to match whatever this the dimension we machined this to. And then this has been bored out till it was almost at the spindle nose to match the through hole of the chuck itself, giving us that much more room to stick large diameter stock back in further. and without running into without disturbing the holes that are here for the cam lock system. So this is the cam lock main stud, the anti-rotation screw hole, and then these are the holes that I put in for mounting the center of the chuck, pulling the face of the chuck back tight against the reference surface. New spin grinder that I built. Instagram followers will recognize this. Documented most of building this and getting it accurate. That's about 3 micro inches TIR on the outside of that 6-inch chuck facial. So it runs pretty darn good. I have the magnet turned on just lightly, just enough to barely hold it on the faceplate there, dusting it off flat. And now I'm going to flip it over and just get the other side so this is parallel. Trying this gray spray-on graphite lube, and there's the layer that it leaves on there. Kind of ideal for the scroll, having no actual liquid or greasy things to attract chips in there. So see how it works. I have the scroll plate in, lubed. I have the scroll backup ring that is meant to screw into the back of this that I salvaged from the original plate. Have G4700 Molykote lube on the all the rotating parts of the pinions, and I have it on the gear teeth. We have the dry graphite spray on the scroll teeth. These are 1/4-inch carbide rods, just because that's what I have that's on size. And this is going to let this piece that is a light press, get aligned rotationally when I put it in. I just have to put some blue moly on the outside. I already have it on the inside here, and then we'll press this together. It's just a very light press, but it's there to support the outer shell. Even though I lubed everything on the scroll on the pilot diameter, I actually tried out the lube system here, putting this into the hole, pressurizing this as I crank it around, and you can actually see the grease try to ooze out through the sides gently as it goes around. So good way to clean out and keep it well lubricated. Same setup as last time, but now we have the stiffener plate inside pressed in here, and same situation. I'm going to release this completely. You can see that I'm zeroed there, and now I'm going to crank up to where I was before, and you can see that is about 6/10 instead of the almost 4/1000 that we had before. I'm putting about the same amount of pressure on. So you can see that really stiffened that whole section up, because now it has to compress this whole plate section. It still has flexibility, everything's still rubber, but we've decreased the deflection by a huge percentage.
At the micro height here, taking measurements of the chuck body assembled with our plate that's pressed in, using a gauge block here to be able to measure a recess, because this probe actually isn't meant to go in recesses at all, but this allows me to get a good reading without doing that. This surface and this surface both bear on the backing plate now, so the step height here needs to be identical if I'm not going to distort the chuck when I put these two bolt patterns are snugged. So over here we have that same height that I've measured, that I was machined on the lathe, and this was the design size. So the error here between this and the other one is about 2/1000, and that means I'll just grind about 2/1000 off of this to match the reading that I have here. While I'm grinding this on the spin table, I will grind this surface until the taper starts to seat and stick on the spindle nose. Right now it's darn close. This seats, and you can't get any shake or play manually on the spindle nose, but this really should be ground until this has just a few tenths, half thousandth gap when you push it on by hand, and then when you use your cams to suck back, this actually forcibly seats on the spindle nose a little bit. Can't go overboard, because then you have a situation where if this doesn't seat, you've really got a bad situation. Then without that facial contact, the chuck will be unstable. So just dust a little bit off of this until that gets snug. I can go back and forth, trial and error until I get that feel, and we'll be good to go. Tapped in the plate on the spindle to run reasonably true. A thousandth or two is plenty good enough for what we're doing here. It has no effect on the facial grinding that we're doing to a degree. Turn the chuck on, and then we're good to go. Grind these other surfaces. This is totally overkill. Not necessarily grinding the height, but the surface finish that's on these. This is ductile iron. Show you the reflection of the indicator there. And this was without coolant. You can see the whole setup here. And then I have a power supply down here that is variable speed. Lets me adjust that. That's at 10 millionths per division on the upper scale there, so it's roughly bumping around about 5-6 millionths. That would be better if I had used coolant to show you that that's the scale it's on. This is erroneous here. That button's not flush. The marker doesn't work. I'm actually on the 10 millionths per division scale. Very handy for parts that hang out over the chuck to pop off the magnetic chuck from the residual magnetism. Now we have the chuck body. I ground the other piece to have the nominal step height. Measured exactly what that was. Now I'm going to kiss the top here so we get a good finish on this, and then drop down to that exact height and grind just the band where this sits. So these two will be a perfect match with each other. I'm zoomed in here on the grind on the outer edge where I was using the traverse across on the x-axis, not the normal z-axis. So you can see that one grind lay is, it's even though it has a little curve in it, one grind lay is like this, one grind lay is like that. And that's from the wheel approaching on two different sides in X. Notice how even that pattern is. There's not one that's more predominant than the other. Now, that is where I'm talking about when you're grinding in this axis. When you're grinding in this axis, that you get your two different cross sides. This side is creating one angle relative to the outside diameter. This is creating the opposite. But if you don't have the axis of rotation of the grind fixture perfectly perpendicular this way to the table travel in the X, you're going to have a place where it's either going to hit on this side and cut air here, or vice versa, and it's going to cut a conical one way or the other, convex, concave. And most grind fixtures are not tweaked in this direction, so beware. Don't think you can just willy-nilly do this on a standard grind fixture, because it's probably not aligned laterally good enough to do what's going on here. To get that pattern, that uniform, that requires it to be within sub-tenth level of alignment over that long distance. Here you can see I'm using the indexing holes that we put in those pieces previously to be able to do a 90-degree index. The bar on the left there is just super glued onto the vice jaw for the x-axis direction stop, and we'll go on from there. Using a torque wrench to get a consistent tightening force on here, since this part sticks up so high. The long box wrench is on there so I can loosen it, because this is a ratchet, so you have to keep flipping the ratchet. So I use this to loosen, and then the torque wrench to tighten. Drilling the tap drill hole. Here's an important machining note, that you have to be conscious of the lever arm that the cutter has against the gripping area, how far away this is. This is getting pretty long, and what that means is the cutter forces here have this huge ratio of lever arm relative to the grip area. That means this if you're not careful, if you're not gripping tight enough or have enough span where you're actually gripping, this is where crashes can occur, because this can peel out. And so that's also why I have the
torque wrench on here. I have 70 foot-pounds of clamping torque on here consistently to have a high clamping force, and to be aware of that, and also not getting carried away with the feed rates. Be aware of this. Here we have the recess roughed out with a 1-inch end mill, and it's going to be bored out to 1 1/16. Chamfering the tap hole with a big 3 Severance countersink. Boring out the 1 1/16. This is the rough pass. Now finish pass. Now physical check with the actual head of the adjuster screw. Oh yeah. Doing that big chamfer there that blends into just about 0 and then back up. Now we're doing the 7/16 40 tap. We've ground our faces to the correct step height on both this piece and the chuck to match each other so they bear evenly on these two surfaces. We've added the bolt circle that pulls the center of the chuck down snug to this, basically increasing the stiffness of the face of the chuck so that the tendency to spring open and for the jaw face to puff out and let the jaws go bell mouth is reduced. These screws are all fitted to the tapped holes. They were gauge fit. They're still a gauge fit, very snug. Some of these diameters had to be trimmed a little bit because of the shift in axis of the tapped hole versus the bored hole. So I did that so that these all fit nicely. These get a needle bearing, the 2 washers and the needle race itself that goes in between here, and the part that sticks up above here is what bears on a recess in the chuck body. And so we are compressing the chuck body to push it around. That's why we put the inner plate. It was a press fit to stiffen that up. And we're going to move on now and do the machining on the chuck body.
Roughing the recess in the chuck body with a 1-inch end mill. Finishing the actual radius size and the depth with a tool that has been ground so that the bottom is perfectly flat. Putting a chamfer on this edge right there on the outside of the radius with the 1 1/4 Severance chamfer tool. Here you see the adjuster screw in location 1 of the 4, and here I'm moving this sideways and I'm checking to make sure that the radius, size, and location that I generated here, to make sure there was room for this to be able to translate. I had an indicator here measuring the offset of the, as I slide the chuck body or the backing plate back and forth. And you can see I've got a good clean 15/1000th of an inch of travel, which I'm not going to use that much. I'm only going to use 10 both directions, but the clearance for the radii is good. There's the overall measurement setup.
Here you can see the previously turned heads of the socket heads, and now I'm using what I call the poor man's screw machine technique to incrementally turn the neck down on these so that there's more room for lateral movement in the holes without binding. And this works very well.
Little belt sander action to get the irregularities off the shaft. You don't want stress risers in there from deep scratches, so just polish this riding on the flexi section of the belt enough to get it smooth. I'm lubing up the needle bearing thrust washers, putting CMD extreme pressure lube on the one side. Then I'm going to fill up the bearing with this from both sides. This needle bearing will never get to the dynamic friction stage. This is always going to be static friction mode. So I'm putting the CMD on there because this is extremely good high pressure, low speed grease, and a little bit on the this side of that bearing, and then I'm putting on the face that's actually going to bear on the shoulder of the chuck. I'm putting GN Molykote assembly grease. This is very, very high pressure stuff. And just running this in. This is just to get the bolt holes aligned. This will get its O-ring and everything when I have the final assembly. I've got the chuck mating surfaces lubed with the Molykote GN grease. I've got these over here, and what I'm doing now is I'm going to put the chuck on here, but I'm going to let and the bearings are on here. I'm going to put this on, and I'm going to come in and touch with the bearings both directions, and that's going to square up where it finds its happy place as far as angular location, because I want to make sure that that's settled before I put the bolts in and firm it down. Otherwise, if you put it down and tightened all the bolts and it was skewed, then these would be hitting off axis. They wouldn't be hitting square bearing wise, so I'm letting them do the alignment first. I'm choosing to use a controlled amount of force holding this chuck body to the backing plate, and I'm just picking a number that I think is going to be plenty. 1,000 pounds per screw. 12 screws, that's 12,000 pounds of actual clamping force distributed over those 12 screws. So I plug in 1,000 pounds force, all the variables for each of these 2 screws, and I come up with 58 inch-pounds for the M8 and 38 inch-pounds for the M6. In the video I talked about using the Moly lube on here, but I found that the extreme pressure lube, CMD extreme pressure lube, actually worked better, and I actually used Teflon pipe tape and laid strips on the top of the grease at each screw location and embedded it in the grease so that it would stay put on all of these locations, then assembled it, and then aligned it as I showed in the video with these screw adjusters, squaring it up to the bearing faces, then snug these down, then torque them, and then later torque them, because the CMD lube and the Teflon both take a while to extrude out because they're so thick and viscous. So I came back and retorqued these, and they all moved just a little bit. That's one of the things that gives that nice smooth motion. That Teflon tape really worked amazingly well. Right here you see the O-ring all gooped up with extreme pressure lube, and you'll see when that starts to climb in the recess there that this should slowly work its way down in and be happy. There we go. Yep, got to be gentle, give it time to actually climb in. Now that's has an O-ring seal around that to keep that clean. I'm no expert at this as far as generating DXF 2D drawings to send over to the laser, but this is what I found to work well in SolidWorks. So I need plus or minus 10 divisions of graduations with half thousandths in between. 25 thousandths is one full revolution. So I do a master sketch, and I'll edit that master sketch so you can see the dimensions. And here I have all these dimensions. This outer rim is larger in diameter than the actual part. The other line below here is the actual part, and that's the laser lines run off the part, guaranteeing that it gets to the edge. And I have all these the line lengths and all that's adjusted, but I don't use that at all for the actual sketch that I'm going to be using. So I save that. What I do then is I do another sketch right on the same plane, but in this sketch all I do is copy the elements of the bottom. So that actually contains only the geometric things that I want to print. And then we'll move on from there. We'll close that sketch and we'll come down and go to the text layout. And here what I've done is I've laid out the lines that are necessary in SolidWorks for the basis of having the text orient around a circle when you're using text in a sketch. There might be easier ways to do it, but I did it this way. And then you see these dimensions here. These are dimensions to change the length of this, which allows me to align the text laterally for each of these positions where the text is. But you'll notice I'm not putting any text in this sketch. This is done, but then I come down, same thing. In this text sketch, I come down here and I use that underlying text geometry for the text elements, and this is so that I can have single line fonts. This is an actual single line font in SolidWorks, and this works really well. And what I do is I use beam wobble. In the case of I did on this a
0.4 millimeter beam wobble, and that gives me a wider line, and I actually traverse slowly, but then I use just single stroke fonts, which works extremely well. So that's what that is for. And then the last one there is just the diameter for alignment purposes that lines up in the center of the hex. Now, the key here is now you can come back here and hide these sketches that are only layout sketches, and you end up with only the lines that you physically want. And now when you do a drawing of this, the DXF only contains this geometry. All the other stuff is hidden. So by being very careful about just using underlying sketches stacked on each other and the ability to turn them off, then when you go to the drawing in SolidWorks, they are not visible and don't get converted in the DXF conversion. So just that might help some. Like I said, I don't think this is probably necessarily the best way, but it's a way that I found to work. So one of the tricky things on this was determining the amount of force that I want these two adjusters working against each other. And basically, with the amount of force I generated with the 1,000 pounds here, I had a consistent drag force where I could find out how much torque it took to break this loose and make it move, basically getting the static friction going and moving. Once I had that value, I put this on. These were not engraved yet, and trued the chuck up in the lathe with a piece of stock in the jaws, and got this to run true with each of these torqued to that correct value and centered at the same time. Once I did that, I took a 30-degree angle gauge here and just drew a pencil line on the face of these adjusters, and they're internally marked on the ends, so I knew which ones are which. Then I put my laser, I lined this up with my laser engraving, the axis of the part, and all I had to do was change which number was which. And so that's how that was accomplished, to get that to line up. And then once I put them in, I lined it again, and then I actually drew or engraved the mark in the chuck body, the chuck backing plate here for the 0 mark. That could be moved if necessary, but really all you're trying to do now is these. The premise here is you move these in conjunction, the same amount of thousandths backed up as you tighten on the other side, vice versa, and you're always keeping the exact same amount of force in the chuck. That combined with the ring that we added, which stiffened the chuck when it's being compressed from the sides immensely. So this chuck is not springy like a buck chuck is, where there's a lot of mush in it. When you can tighten it more and more and more, which is bad practice, but basically it stretches all around. This is much more solid. So this isn't the be-all end-all. If I was going to make one of these chucks from scratch, I would actually make this outer chuck body here be all the way out like this, continuous, so that the needle bearing would bear full face, and then the chuck backing plate would actually be captive with a bolt-on lip where everything's ground very precisely, where it's just a gauge fit, where there's no bolt holes actually holding the chuck there. There's no nothing but a gauge fit of an overhanging tongue like this, where it can move. The chuck can move on a flange. And that's how Dan Gelbhardt's adjustable chuck is done. And his is kind of a more advanced version of this, where the control of these two screws, or the two moving systems, is coupled together. So if I could get this to magically engage with that screw over there clean through, it would accomplish the same thing. This would actually move, and the other side would move, and the amount of compression of the adjusters would remain same all the way through the travel. In this case, I'm just doing it manually. If you tighten this 1,000th, you have to loosen the other one 1,000th, and you just keep track of it. And since you only have 10,000ths of travel either way, very easy to do. So I hope you enjoyed this, and I'll be back.